Right, ion propulsion. The xenon ion drive, where xenon ions are propelled by a high voltage 20,000 volts. What speed do they reach? It's not a SUVAT, it's an energy conservation. If you recall that the energy gained by a charge that moves through a voltage is equal to QV, that energy is converted into kinetic energy. So we can express V as the square root, where this is the voltage, this thing, and that's the velocity. 2Q times the voltage divided by M. So the square root of 2 times 1.6 times 10 to the minus 19 times 20,000 divided by the mass. Oh gosh. What is the mass? Well, they've given us the atomic mass of xenon. That's grams per mole, isn't it? 0.131 kilograms. Divide that by Avogadro's number. So let's put that into our equation. So it's going to be 20,000 divided by 0.131 times Avogadro's number. And that gives us 171,000 meters per second. Wow, that's quick. But what impulse is provided by 1 kilogram of xenon? Well, the impulse is the change in momentum going from 0 to 171,200. So it's simply the same number, 171,200, where the mass is 1 kilogram. What's the maximum speed of a spacecraft that burns 25% of its weight as xenon fuel? Okay, so the spacecraft is going from 100 down to 75% once it's burned all the fuel. So the average mass is going to be 82.5, I think. That's the average mass of the spacecraft in percent. Let's call it kilograms to make life a bit easier. So I start off with a 100 kilogram spacecraft. Its average mass is 82.5 kilograms. The change in momentum of the fuel is going to equal the change in momentum of the spacecraft. So the fuel, which we know is 25 kilograms, that's going to leave the spacecraft at 171,200 meters per second. That momentum is going to be equal and opposite to the momentum of the spacecraft. So I do 171,200 times 25 divided by 82.5. That gives us 51,880 meters per second. So it's a little bit less than the exhaust velocity. Assuming the average speed is half of the above, calculate the time taken to reach the nearest star. So because we start at 0 and the spacecraft kind of speeds up uniformly, so the average speed is going to be half, 25,940 meters per second. Now, at the speed of light, it takes 4 years. So we're going to have to divide it by the speed of light and times it by 4. So 25,940. Let's just clear a bit of space and explain why. So let's take an easier example. If the average velocity had been 3 times 10 to the 7 meters per second, then we know that would have taken 40 years. We would have done 3 times 10 to the 7 divided by 3 times 10 to the 8. Sorry, the other way around. 3 times 10 to the 8 divided by 3 times 10 to the 7. So don't need that. Now, and then we would have multiplied that by 4. So just to see where that comes from, if it had been 1/10 of the speed of light, we would have taken 4 times 10 light years. Now it's not 1/10. It's 25,940. So the speed of light divided by that answer times 4 will tell me how many years it takes, which is 46,260 years. That's not very well written, but anyway, you get the idea.